Welcome back to Formula in Motion. In the previous video, we talked about work and kinetic energy. We saw that work is the dot product between the force vector and the displacement vector, and in the more general case, it can be written as the integral of the force along the path. Kinetic energy, instead, is given by 1/2 mv squared. It is the energy associated with the motion of a body. The work-energy theorem tells us that the change in kinetic energy is equal to the total work done on the body. So work can be understood as a measure of energy being transferred to or from a system. But motion is not the only way energy can appear. Energy can also be stored because of position, configuration, or interaction. And this brings us to the other central idea of this video, potential energy. By definition, potential energy is the energy associated with the position or configuration of a system. And this already sounds less intuitive than kinetic energy. Kinetic energy is easy to imagine. Something moves, so it has energy because of its motion. Potential energy is more subtle. It is not directly associated with speed, but with the way a system is arranged. A body at a certain height above the ground, a compressed spring, two electric charges separated by a certain distance. In all these cases, energy is stored because of the configuration of the system. To define potential energy, we need a special kind of force, a conservative force. A conservative force has a very useful property. The work done by the force does not depend on the path taken. It only depends on the initial point and the final point. So if we move a body from point A to point B, the work done by a conservative force is the same no matter which path we choose. This is what allows us to define a potential energy. The simplest example is gravity near the surface of the Earth. If we choose the vertical direction upward, the gravitational force can be written as F equals minus mg, where m is the mass of the body and g is the gravitational acceleration near the surface of the Earth, approximately 9.81 meters per second squared. The minus sign tells us that the force points downward. To this force, we associate the gravitational potential energy, V equals mgh, where h is the height of the body measured from a reference level. This reference level is called the zero of potential energy, and it is arbitrary. We can choose the ground as 0, a table as 0, or any other height. What matters physically is not the absolute value of potential energy, but its variation. So, intuitively, the higher the body is, the greater its gravitational potential energy. Another important example is the elastic force. For an ideal spring, the force is described by Hooke's law, F equals minus kx, where k is the spring constant and x is the displacement from the equilibrium position. Again, the minus sign tells us that the force always points back toward equilibrium. If the spring is stretched, the force pulls it back. If the spring is compressed, the force pushes it back. To this force, we associate the elastic potential energy, V equals 1/2 kx squared. So the farther the spring is from its equilibrium position, the more potential energy is stored in the system. There is also a deeper mathematical relation between conservative forces and potential energy. In one dimension, this relation is F equals minus dv dx. This means that the force is related to how the potential energy changes with position. The force points in the direction in which potential energy decreases. In more dimensions, the same idea becomes F equals minus nabla V, where nabla V is the gradient of the potential energy. The gradient tells us how a function changes in space. So this formula says something very powerful. A conservative force can be obtained from the shape of the potential energy. Let's see this with the elastic force. For a spring, we know that F equals minus kx. But for a conservative force in one dimension, F equals minus dv dx. So we can write minus kx equals minus dv dx. If we multiply both sides by minus 1, we get kx equals dv dx. Now we integrate both sides with respect to x. The integral of kx is 1/2 kx squared. So we obtain v equals 1/2 kx squared plus a constant. And if we choose the equilibrium position as the zero of potential energy, that constant becomes 0. So we recover the elastic potential energy, V equals 1/2 kx squared. Once kinetic energy and potential energy are clear, we can introduce mechanical energy. Mechanical energy is defined as the sum of kinetic energy and potential energy. E equals K plus V. This formula is extremely important because under the right conditions, this quantity remains constant. If no external work is done on the system, and if only conservative forces are involved, then the total mechanical energy does not change. K plus V equals constant. This means that energy is not disappearing and it is not being created. It is simply changing form. Sometimes it appears as kinetic energy, sometimes it appears as potential energy, but the total amount remains the same. Imagine a ball falling from a certain height. At the beginning, the ball has gravitational potential energy because its height is not zero. If we assume that the ball starts from rest, then its velocity is zero, so its kinetic energy is also zero. But as the ball falls, its height decreases, so its potential energy decreases. At the same time, its velocity increases, so its kinetic energy increases. The energy is not lost. It is transformed from potential energy into kinetic energy. Just before reaching the ground, if we choose the ground as the zero level of potential energy, the potential energy is minimum, while the kinetic energy is maximum, because the ball has gained speed during the fall. We can also understand this result starting from the work-energy theorem. The work-energy theorem tells us that the total work done on a body is equal to the change in kinetic energy. L total equals delta K. But for a conservative force, the work done by that force is equal to minus the change in potential energy. L conservative equals minus delta V. If only conservative forces are doing work, then the total work is the work of the conservative forces. So we can write delta K equals minus delta V. Now we expand both terms. K final minus K initial equals minus open parenthesis V final minus V initial closing parenthesis, which becomes K final minus K initial equals minus V final plus V initial. Now we rearrange the terms. K final plus V final equals K initial plus V initial. And this means E final equals E initial. This is the conservation of mechanical energy. Before closing, it is worth asking what happens when non-conservative forces are present. The classic example is friction. When a body moves along a surface, friction acts against the motion, and because of this, it does negative work on the body. This means that part of the mechanical energy is removed from the motion of the system, but it does not disappear. It is transformed into other forms of energy, mainly internal energy and heat, which are then dispersed into the environment. So, in the presence of non-conservative forces, mechanical energy is no longer conserved. In formula form, we can write delta E equals LNC, where LNC is the work done by non-conservative forces. If LNC is negative, as in the case of friction, the mechanical energy decreases. But this does not violate the conservation of energy. It simply means that mechanical energy is only one part of a bigger picture. A more general way to express this idea appears in thermodynamics through the first law, delta U internal equals Q minus L. This law also takes into account heat, internal energy, and energy exchanges that are not purely mechanical. So mechanical energy may not always be conserved, but energy itself is never lost. It only changes form. And with this, we have connected kinetic energy, potential energy, mechanical energy, and the role of non-conservative forces. If you enjoyed the video, consider subscribing and leaving a like. Thanks for watching, and I'll see you in the next video.